Hi, everyone. Let's see. So I'm going to start with some residual questions that are left after what we talked about yesterday, which is we looked at how to calculate the spectral form factor in JT gravity. And we found that if you include this space-time wormhole contribution, linking the two copies of Z of beta plus IT, we found that gives the ramp that we would have hoped to find in the spectral form factor. Some residual questions are, where's the plateau? Do we have to sum over more complicated space-times with more complicated topologies? Also, where's the noise? For a given Hamiltonian, not averaged over Hamiltonians, if you try to calculate the spectral form factor, you expect to get a noisy function where you only see this ramp and plateau after averaging over different Hamiltonians or averaging over time windows or something like that. We might have hoped that JT gravity is dual to a theory with a single Hamiltonian, and in that case, you would have expected this noise. And then furthermore, why is Z of beta plus IT squared not equal to the square of beta, Z of beta plus IT? So by that, I mean, if you try to calculate the spectral form factor, you do a path integral with two boundaries, and you find this wormhole link in the boundaries. So that wormhole only appears when you try to calculate this two boundary quantity, and it doesn't appear if you try to calculate Z of beta plus IT by itself, and then square the answer that you get. So these three questions are sort of what we're going to be talking about today in JT gravity specifically. And let me give a little bit of background from the late 80s on space-time wormholes. So again, this double cone or the cylinder that gives a ramp is an example of what's called a space-time wormhole that links distant regions in space-time for different asymptotic boundaries. And as I just said, these space-time wormholes can obstruct factorization of things like partition functions. And this was pointed out by Maldacena and Mayos in the 80s CFT context. But there's another way you can try to interpret this answer. That when you calculate two Z's, you find a wormhole. And when you calculate Z by itself and square it, you don't find a wormhole. You can think of Z as behaving something like a random variable, where the things that we're calculating with the path integral are expectation values of that random variable. So this is the case in random matrix theory, where Z is averaged over Hamiltonians. So this interpretation of the gravity path integral with space-time wormholes as giving some sort of random average goes back to the 80s with work by Coleman and Giddings and Strominger. And so what they did is they considered the Euclidean path integral for gravity, and they thought about what would happen if you included like tiny Planckian wormholes that link distant regions of this Euclidean spacetime. So let's focus on a single tiny little wormhole that links distant points X and Y. So what they did is they said, if you try to integrate out this wormhole, you can replace it with an effective coupling between points X and point Y. So it's a non-local, it's a non-local coupling between X and Y, and we can think of it as like inducing this coupling, which is the sum over local operators OI, O at X, O at Y, times some coupling constant for I. And so what this means is that if you take the theory with wormholes and integrate it out, you can write a Lagrangian for the theory without wormholes, where you have your normal Lagrangian that doesn't have these bilocal couplings, but you add on this bilocal term. So here I have this sum over the different local operators OI, and I'm integrating over the possible points X and Y, integrating independently, because the two wormholes can basically be independently, they have their endpoints put anywhere independently. So this is because of this small wormhole approximation, the two endpoints don't really feel each other unless they get very close. So we can approximate it as completely bilocal. So
I have a question, sorry. So this extra term involving the two operators, is this the same as the double trace deformation that I've heard about, which involves traversable wormholes?
Oh, it's different than that one. That's like you can think of it as an addition to the Hamiltonian. That would be so here this is integrated over space-time and space-time. That would just be a term in the Hamiltonian. Where there's in the Lagrangian it would have one time, but it would be non-local in space. Maybe that's how to differentiate them.
Okay, thank you.
Okay, so we can take the path integral for the theory with this funny bilocal term induced by the wormholes, and we can write it in this way. We're going to undo this square by introducing some variables, just some random numbers alpha I, which we integrate over with a Gaussian weight. So if we do this Gaussian, we have an alpha I squared, and we have this term here, which is a local coupling for OI with a term proportional to alpha I here. So if we do this Gaussian integral over alpha I, we complete the square, we end up back with this term here. So this thing in the brackets here, this is like a local theory. We have our old Lagrangian, but we've added this new local term with couplings alpha I. And then we can think of the alpha i's as just random couplings that we're averaging over. So the theory with the wormholes looks like an average of theories without wormholes, but instead having random local couplings. So this sort of idea that a theory with wormholes looks like some sort of ensemble average of theories without wormholes has been refined somewhat in the ADS-CFT context by Muralf and Maxfield somewhat recently. So back in the day, when Coleman, Giddings, and Strominger were thinking about this, they weren't thinking about ADS-CFT. It hadn't been invented yet. But now these sort of ideas are appearing back in this new context. And so what we're going to be really focusing on today is how JT gravity gives an example of this phenomenon. JT gravity, where we include all the space-time wormholes, is dual to an average over theories. And so basically everything I'm going to be talking about today comes from this paper by myself and Steve Schenker and Douglas Stanford. So precisely the statement is that if you calculate these partition functions in JT gravity, so it's a path integral with boundaries of length or normalized length beta 1 through beta n. So an example would be z of just one beta is the partition function. Z of beta 1, beta 2 is something like this spectral form factor. It's got two boundaries. I'm going to consider the general case with n boundaries. And we sum over all the spacetimes that can possibly link the different boundaries and have all sorts of handles and any sort of topology. So this quantity, the claim is that it's equal to an average over Hamiltonian's H with some random matrix distribution P of H of trace e to the minus beta H. So this is just the normal partition function for fixed H. We take a product of those and we average over the Hamiltonians with this distribution. And so in the picture here, try to represent this linked thing that the path integral for JT gravity gives is equal to an average of sort of decoupled partition functions with fixed Hamiltonians. So one output of this is that in JT gravity, we did this calculation with the spectral form factor. We didn't find noise, but actually because we're now going to be interpreting that path integral as an ensemble average of theories, we wouldn't have expected noise in the first place. We'd just expect these average features like the ramp and plateau. Okay, so because we're going to show that JT gravity is described by a random matrix theory, random matrix integral, we're going to start by talking about solving some more general random matrix theories, more general than the ones we talked about a couple days ago, which was the GUE. So the generality now is that instead of having a quadratic potential for the matrix, we have a general potential, V of H. So this probability is e to the minus L. L is the number of eigenvalues times trace V of H. And this does fall into the so-called GUE symmetry class that we talked about the other day, because this potential here is unitarily invariant. It only is trace of V of H. So this is invariant under H goes to U dagger HU. Depends only on the eigenvalues. So the things we're going to be interested in are the partition functions, so averages of products of partition functions. But in fact, just technically, it's useful to study the resolvent instead of the partition function. Resolvent is trace 1 over e minus h. It has poles at the locations of the eigenvalues of h. So here I'm using lambda to describe the eigenvalues because I don't want to use too many e's. So e is like the external energies and lambda is the eigenvalues. And then this resolvent here, we can relate it to the density of states by taking its discontinuity across the real axis. So we're interested in z of beta, but we're really going to focus on the resolvents or the densities. We can go back and forth between them using integral transforms. So we know these, if we know how the correlation functions of these behave, so averages of products of those, we know how averages of products of these behave. So to get an idea of how things are going to work, let's think about just doing perturbation theory in this matrix integral. We'll do Feynman diagrams. So let's write out trace v of h. V is we can write as a polynomial in h or some power series. And let's ignore that. Let's imagine we don't have a linear term for simplicity. We have a quadratic term, we have a cubic term, some coefficients. And we can imagine trying to do Feynman diagrams where we treat this as giving a propagator and these are vertices. And if we use 't Hooft's double line notation, here's some representations of the propagator, where the black lines represent Kronecker deltas enforcing index contractions. So we have a propagator, and we also have something like a cubic term coming from this trace h cubed term. And if there's a trace h fourth or trace h fifth, those will give higher order vertices with the more outgoing legs. And so if you calculate something like some product of traces in this matrix integral, and you try to do it by Feynman diagrams, as 't Hooft taught us, we can think about classifying the Feynman diagrams by the topology of the surface which is tessellated by a given diagram. So here there's a contribution to a 3 trace thing. So trace h to some power, trace h to another power, trace h to a third power, where we have a circular boundary because all the h's are connected together, contracted together with their neighbors through this trace. And then the Feynman diagrams calculating this average of 3 traces, they'll connect together the different h's in these 3 boundaries, and we can think of them as forming some surface, some topology. And if you count the index loops in this diagram, so remember there's L, this is an L by L matrix. So if we have an index loop in this diagram, it contributes a factor of L. As 't Hooft taught us, the number of index loops is related to the topology of the given diagram. So that diagram with a given Euler characteristic comes with a power of 1 over L to the minus chi of m. So what this means is that we can organize the calculation of resolvents. Here I'm writing the connected part, where we subtract off the 1-point functions or fewer point functions from this thing. So we only include diagrams which connect all of the boundaries. We can express this resolvent correlation function as a sum over the different topologies which contribute to it. And here, because the number of boundaries are fixed, we sum over the genus of this surface. And here, each R or G sub n, where G is the genus, n is the number of boundaries, is given by the sum over all diagrams with that given genus. And here I've written a squiggly equals to because this is actually in general an asymptotic series. It doesn't converge. So with this idea in mind that we're going to study these resolvents in this 1 over L genus expansion, let's define the density of states, or the average density of states, rho naught of E, as this, where we take the density of states normalized. So it's the sum over all the delta functions at the locations of the eigenvalues, divide by L, so it's normalized, and take the L goes to infinity limit. So this is like the large L density of states, some continuous function of E. a couple of lectures ago, I used a little bit of a different notation that maybe I regret, where I had a tilde on this to denote that it was normalized. So in that case, in the GUE, this would be the semicircle formula. But now we're considering more general matrix integrals, not just this GUE, which gives a semicircle. But what we're going to do is not be too general. We're going to restrict our attention to a simple case where it's called a one-cut matrix integral. The density of states has support only on some interval with endpoints, let's say at A minus and A plus. So here's just a picture of an exact example density of states on this interval. So this rho naught of E is the leading order piece in the 1 over L genus expansion of the density. And so it's related to the leading order piece of this resolvent here, where I've labeled R again by the genus and the number of boundaries. So the leading piece has genus 0. It's just this disk here. And so just to get an idea of how to deal with these matrix integrals a little bit more generally, let's try to solve for R01 in terms of this potential, the general potential for the matrix integral. That from then we'd be able to extract this density as a function of the potential. So the strategy we're going to take is a little bit similar to what we did a couple lectures ago to find the semicircle. What we do is we write an effective potential for the eigenvalues, where there's a potential V of lambda and this term which comes from the van der Waals determinant for the eigenvalues. And we can think of taking this continuum limit where we replace the discrete sums over energies by integrals weighted by the density of states. And from this action, we can get some equations of motion for the eigenvalues. This equation of motion we can get by varying lambda I here and setting equal to E, and then taking the continuum limit. Or we can think about it as varying with respect to rho here, and then taking the derivative with respect to E. And this equation of motion is just saying that if you have an eigenvalue at energy E, the forces from the potential balance the forces from all the repulsion from the other eigenvalues. And so this equation of motion here, V prime, is this integral. This right-hand side looks like the resolvent, but it's got a principal parts prescription for this integral. That just becomes from the fact that we don't sum over energy I equals energy J in this van der Waals term. But if we take this principal part prescription into account, we can think about this side as just the sum of the resolvent across the real axis. So we have this equation here. So this by itself is not particularly useful. But there's a trick. And the reason I'm going to tell you about this trick is just to sort of illustrate some of the general ideas that go into solving some of these matrix integrals. So these tricks that we'll use to solve the matrix integrals, they all have to do with taking advantage of the analytic structure of the resolvents. And we'll see here is one way how it works out. So let's define a function sigma of x, which is x minus, x minus a plus. Those are the endpoints of the support of the density of states. So let's say we know what those are, so we can compute sigma. We'll later show how to solve for these. So square root of sigma of x, it is going to have branch cut between a minus and a plus. So in the x plane, it's just along the real axis from a minus to a plus. Now we can write the resolvent, or this piece of the genus 0 piece of the resolvent, using Cauchy's integral formula. So here we integrate over lambda around E, where we have to take E to be somewhere in the complex plane away from the real axis. So on the right here, I've drawn the lambda plane that we're integrating over. Here's E somewhere off in the complex plane, and we're integrating around E. So that just picks out the pole, and we get this. So the next thing we can do is deform this contour past infinity to surround this branch cut. So now, why is there a branch cut? There's a branch cut because of this this sigma of lambda here, and we know that the branch cut goes from minus a to, or from a minus to a plus. Okay, So then the final thing that we do is we say, okay, we're integrating above the branch cut here, below the branch cut here, and the integrand has this resolvent in it. That just picks up basically the average of this resolvent across the branch cut. So the discontinuity drops out, the average of this across the branch cut remains. But we just derived a formula from this equation of motion for the average of the resolvent across the cut. So that lets us replace this resolvent with the derivative of the potential. Okay, so now we have this formula for the resolvent in terms of this integral of v prime, but it's also got sigma in it. And sigma depends on a plus and a minus. We don't know those yet. But by considering sort of the large E behavior of this formula, which is, we take advantage of these facts that the resolvent as defined has to go like 1 over E at large E, sigma goes is E at large E. We can write these two equations, which are independent of E, two equations that fix the two A's, and then once we know the A's, we can plug them into this to solve for this. Okay, so that was how we found, that's how to find this leading order piece of the resolvent in terms of the potential in this, using this general formula that it looks like it's just pretty hard to solve in general. And notice that this is somewhat different than how we calculated the semicircle in the GUE. There we could do some things more explicitly, it wasn't so involved. So we can also try solving for the pair resolvent correlation function at genus 0 using a different method. And I'm not going to go into detail for this with this, but I'm just going to tell you basically that there's some other technique you can use, and it works for general potential. And in the end, you find some formula for the pair resolvent correlator. This is related to the pair density function that we talked about. And we see that an answer that looks something like this 1 over E minus E prime squared thing. That's supposed to give the ramp. And there's this other term which sort of doesn't matter for typical values of E, but it depends only on the locations of the endpoints of the density. So the important thing about this that I'm just going to point out is that it only depends on the potential through the locations of the endpoints. It doesn't care too much about the potential. So in that sense, it's somewhat universal. Okay, so far I've showed you two ways that were somewhat very different of calculating different pieces for different resolvent correlators. And that might seem not great because we want to solve the matrix integral. We have to come up with these different tricks for each case. And fortunately, it turns out that you can actually find a more uniform procedure that works for all components of the resolvent, for all the terms in the genus expansion. The starting point is what's called the loop equations. And so the loop equations come from saying you take this integral here, integral over the eigenvalues, where the integrand is a total derivative, so it's equal to 0. And the integrand is like this thing, 1 over E minus lambda I, times some products of resolvents times the e to the minus effective action. This has a Vandermonde, it has the potential. And so if you consider different numbers of resolvents in here, you get different sets of equations that it'll give you information about different resolvent correlators. So if we just take this thing, we work out the derivative acting on each of these terms. So this derivative acting on here, oh, sorry, let's take the case k equals 0 first, so we don't have any extra resolvents. We just have this term and we have the effective potential. So the derivative acting on this gives this term. The derivative acting on the effective potential has a contribution from the Vandermonde and a contribution from the potential itself. And then so we can write this equation in this form and rearrange and symmetrize things and find this equation. So there's a square of the resolvent, and then there's this thing which is depends on the potential. So this is an example of the loop equations. What we can do to make use of this is we can work this out. We can express this thing as a sum over genus and look at the equation genus by genus. So the leading order term in the genus expansion of this equation has to do with this resolvent that we just calculated through this other method. And it relates it to the potential in this way. So actually solving this equation explicitly is not in general very useful. What we're going to do is we're going to point out a specific fact about it that's pretty important. So here on the right-hand side, it's a function of E that is single valued in E, because we're assuming that the potential is analytic in E. On the left-hand side, we have the square of this thing. So we have, let's call this thing in the parentheses y. So we have an equation y squared equals some single valued function of E. What that tells us is y is a multi-valued or double valued function of E. So it's going to have some square root branch cuts where f of E equals 0. So this function, the spectral curve, which is just like a shifted version of the resolvent, it's in general going to have this square root branch cut behavior. It's discontinuity, for example, if you look at this discontinuity, you can show that y is just proportional to this density of states, the leading order density of states. So this is a bit abstract. Let's look at a specific example. If we take the GUE, where V is this quadratic potential, we can evaluate the right-hand side of this equation. It's pretty simple. We have V prime squared, which is just E squared, minus this thing, which is equal to 1, because all these terms cancel. So y squared is this thing. Take the square root, y is this semicircle. Okay, so the points to take away from this are that if you look at these loop equations for the matrix integral, on the right-hand side of these loop equations, you'll be able to write things which are like single valued in energy. On the other side of the equations, you'll have things involving the resolvents, where these resolvents will have some analytic properties like this resolvent y is double valued. Other resolvents, you can make some arguments about their singularity structure. And so using these loop equations and some tricks that are similar to the thing that we did with these changing around all the contours on this page, you'll be able to basically eliminate these unknown terms, which are hard to calculate because they're single valued. And I have some examples written down here. For example, solving for the genus 1 contribution to the resolvent. I don't really have too much time to go into it. For anyone who's interested, so this is an interesting example where we use tricks similar to how we found the leading order density to refine the loop equation, get rid of the sort of annoying term here, which is in general hard to calculate, and just use the analytic structure of these resolvents to write a formula for the genus 1 contribution of the resolvent simply in terms of these other quantities. So here, this is the genus 0,2 resolvent thing, which we found a formula for. And here is this so-called spectral curve. This is the leading order density. So the remarkable thing is that if you take these loop equations and process them in this way, as it was done by Einar and these others, you can actually find that the loop equations turn into nice recursion relations for the genus G resolvents in terms of just the leading order density of states, or this y, and this 2 resolvent thing, which is this universal function that I talked about. So instead of having to know the potential explicitly, you can take these loop equations, process them in this way, and give the density of states instead of the potential to solve for these higher order resolvents. So this becomes particularly useful when we try to study a particular kind of matrix integral, which is called double scaled matrix integral. So basically, this is about what this double scaling is about, is taking L, the number of eigenvalues, to infinity. So the reason we want to do this is we're interested in looking at a matrix integral which describes JT gravity. So JT gravity has this density of states, the sinh of square root of E, and that grows forever. And so if you look at the integrated density of states, there's an infinite number of eigenvalues. So if you try to make a matrix integral with an infinite number of eigenvalues, you have to sort of think about it as regulating an integral with finite number of eigenvalues. So for example, we can think about a matrix integral where we choose the potential so that the leading order density of states is this function, which is like sinh of some semicircle. So here I've drawn a picture of it. It's like a finite, it's one of these one-cut densities that we have been talking about, where here for near the edge, it looks like sinh of square root of E. It looks like JT gravity. But for high enough energies, it starts to deviate, and we see that it actually goes back down to 0. So there's a finite number of eigenvalues. But if we take this density of states and take, we shift E so that the edge is at 0, and then take A to infinity, the right edge of the spectrum will go off to infinity, and the density of states will approach this JT gravity formula. So in this limit, there will be an infinite number of eigenvalues, but the density of states at a fixed energy stays finite. So that's okay, because so what we've been talking about is this 1 over L expansion for these matrix integrals. And you might think, okay, in this case, we're taking the L goes to infinity limit, so that expansion should become trivial. Well, it turns out that the right way to think about it is not so much as a number, 1 over number of eigenvalues expansion, but 1 over density expansion. So in these finite L matrix integrals, the density is proportional to L. So a 1 over L expansion is like a 1 over density expansion. But in these double scaled integrals, you find just a 1 over density expansion. So here, I've written an expansion for the resolvents in terms of powers of e to the s naught. I'm doing that because here we're taking the density of states to be proportional to e to the s naught. So in JT gravity, this came from the topological term in the action. So the density of states comes from the disk, which is just proportional to e to the s naught. What we're going to do is we're going to consider a matrix integral where we choose the leading order density, rho naught, to look like this thing. So this determines this function y I'm talking about. Where now we're thinking about e to the s naught as just some constant number, some parameter that's sort of proportional to L in a limit. Okay, so if you think about this double scaling limit of matrix integrals, you have to tune the potential in a specific way so that the density stays finite in the L goes to infinity limit. And often it's somewhat complicated in terms of the potential. So if we want to study a double scaled matrix integral that gives the JT gravity density of states, it's actually very difficult to find out what the potential is. But as I've just shown you, you can deal with these matrix integrals, you can solve them without actually knowing the potential explicitly. You can use these recursion relations to to give a formula for the resolvents just in terms of the leading order density. And that side note is that you need the leading order density and also this R02, but in this double scaled limit, R02 becomes particularly simple, and it doesn't depend on the endpoints at all. Basically because one endpoint we're fixing at 0, and the other endpoint we're sending to infinity. Okay, so one last thing I'll say about these matrix integrals is that if you take these recursion relations that I mentioned, and you take the double scaled limit, they have a particularly simple refinement called topological recursion due to A nard. So again, the topological is because we're relating terms in these resolvents which are related to diagrams of different topology. So I've told you that these resolvents, for example, y is a double valued function of e. If we define a z to be z squared equals minus e, the y and all the resolvents are single valued in z. So z is a nice number instead of e to use for these quantities. So we take this rho naught of e to be this JT gravity density of states. It's just a sign of z in that z coordinate. And then another convenient thing, it's not terribly important, it's just if you want to study the resolvents, it's a little bit easier instead to think about these rescaled versions of them called the W's. So this is the W genus G end boundaries is related to the resolvent with genus G end boundaries. Okay, so what Einar did is he found this nice formula for the genus G n boundary resolvent in terms of other resolvents that are somewhat simpler. And so basically this is the general form of these recursion relations that I told you about earlier, where we had some contour integrals for those formulas. They turn into these just taking residues. And the important thing to notice about this recursion relation is that the genus G n boundary resolvent can be written in terms of the genus G minus 1 term, more boundaries, and a product of resolvents where the genus for these two guys sums up to G, and the number of boundaries sums up to n plus 2. So you can sort of interpret this as saying the genus G resolvent has a contribution where you think about forming it by splitting a handle on this on the surface which gives this resolvent, and pieces where you glue two different surfaces together. Two simpler surfaces are glued together to form this one. So again, these recursion relations are saying make a more complicated surface or a more complicated topology contribution to the resolvent out of simpler topologies. So to summarize everything that we need to know about these matrix integrals is that if we want to solve a double-scaled matrix integral, all we need to do is specify the leading order density of states, which is just this spectral curve y. And then we can plug y into the topological recursion to get the resolvents or these partition functions of genus G. And then this topological recursion comes from refining the loop equations using just general analytic properties of these resolvents. Okay, so with that, that's how to solve a matrix integral. In particular, how to solve a matrix integral where we have the leading order density of states equal to the JT gravity disk density of states. In those computations, we summed over these Feynman diagrams of any topology. And so we want to do the analogous thing in JT gravity. So in JT gravity, we're going to consider the n boundary partition function, and we're going to write it as a sum over topologies. And the sum over topologies is an expansion in e to the minus s naught because of this topological term in the JT gravity action. So a surface with the Euler character chi is suppressed by e to the s naught chi. So here's a little example, 3 boundaries, and I have some surface in the middle that has a handle on it. And again, in JT gravity, we're only summing over surfaces with constant negative curvature. So there's this integral, so even this integral over these complicated topologies turns out to be somewhat tractable because we're not integrating over any old metrics here with horrible, crazy topologies. They're metrics with constant negative curvature, and those have some known properties that we'll take advantage of. So just physically, what is this? What are we doing when we include all these complicated topologies in the JT gravity path integral? Well, these different topologies, we can think about them as adding on space-time wormholes. Now, unlike the case where that was studied by Giddings, Coleman, and Strominger, these aren't little microscopic wormholes, they're maybe macroscopic. And then in Lorentzian signature, we can think about them as describing the joining and splitting of big universes from these JT gravity spacetimes. So our approach to dealing with the summing over all these topologies in JT gravity is to decompose a given spacetime in a special way. So if we calculate, say, one partition function in JT gravity, it's a contribution with, say, 2 handles. We can take this spacetime and cut along a geodesic, a circular geodesic that's right here. And this is like the cutting that we did yesterday when we were describing the ramp in the spectral form factor. We cut along a geodesic of size B, and we can furthermore decompose this handled surface by cutting over more geodesics. So we can split apart this thing into pairs of pants. So you can always make this sort of decomposition, where you take one of these general contributions to JT gravity, split off these trumpets by cutting along some circular geodesics, And then furthermore, you can split this thing. This thing has circular geodesic boundaries. You can split that apart into pants. So the action of JT gravity is independent of the shape of this pants, so the moduli of the surface. That's because the JT gravity action has a topological term, and has a term which sets as a delta function constant negative curvature, and it has this boundary action, the Schwarzian term. Now, the boundary action, it actually depends on the size b of this circle in the trumpet, just because as you change b, it changes the radius at where this regularized boundary is. But it doesn't depend on the parameters of the handles out here, only on this b circle. So we can write the path integral over a surface like this in the following way. So we take the trumpet here. So the path integral over all these geometries with the wiggly boundary, but a fixed circle B here. We multiply it by the sum over all surfaces with this B circle here. So we integrate over all the moduli of this handled surface for fixed B. And then we integrate over B with some measure mu. So to do this path integral, we need to know first, what is this thing? What is the trumpet with fixed B? That's an integral over the boundary curves for fixed B. What is the measure for integrating this B? And what is this thing here? This, what's called the volume of the moduli space of ordered Riemann surfaces, genus G and N boundaries, geodesic boundaries, B1 through Bn. So here's a special case. I have genus 2, 1 boundary. It's a function of B. Now, I'm actually not going to be able to go into much detail about how to find these, how to calculate these various quantities. You can see section 3.3 of this paper for more details. But here's the main idea. To know how to calculate all these three things, this volume of the moduli space of Riemann surfaces, the measure for B, and this trumpet, we need to know the measure of integration over the boundary curve. We need to know the measure of integration for B. We need to know the measure of integration for the moduli. So we can think of JT gravity in the first order formalism with the Vielbeins and the spin connection as a SL2R gauge theory. It's a certain type of topological BF theory. And the point there is that when you view JT gravity as this BF theory, it's an integral over gauge fields, there's a natural measure for the gauge fields that comes from the symplectic structure, symplectic form on the space of the gauge fields. So the measure is derived from that symplectic form. And then from that measure, you can calculate this integral of the trumpet. So there's a measure for the integral of the shape of the boundary. And it turns out to be one loop exact, much like the disk path integral that I talked about yesterday. The measure for the integral over B, when I glue the trumpet, it's this measure that I mentioned briefly yesterday. You integrate over the size of B and also the distance you twist by when you glue together. The distance is tau. Now, when you glue B, the trumpet to this surface, it's independent of the twist, so we can just think about integrating over the twist angle from 0 to B, and you get BdB. And this measure here over this twist and size is called the Veit-Petersson measure. And also, when we glue these pants together, we can think about the pants as having a circle of size B, and we glue them with some twist, and we integrate over the B and twist of each gluing with the same measure, the same Veit-Petersson measure. But we have to be really careful. So if you take a surface like this, decompose it into pants, you write it as an integral over pants glued together with this measure here. You're not freely integrating over the B's and the taus. That's because the way of the decomposition of this surface into pants is not unique. So if you try to integrate freely over these lengths and twists, you'll overcount. So this is analogous to, like, a way to think about this is, it's very similar to how if you try to form a torus by gluing together a cylinder, you have to integrate the length and twist over a fundamental domain. So in general, this integral is very difficult to do. In fact, in practice, even doing the simplest case where you have one boundary and one handle is extremely difficult. So just basically dealing with this overcounting problem is very difficult. There's some terminology that's really not too important to go over. So altogether, in terms of these unknown quantities, these volumes of the moduli space of these Riemann surfaces computed via this difficult integral, we can write the path integral for the genus G contribution to the n boundary partition function like this. So we have a bunch of trumpets, we have n trumpets, and they're glued to this surface, which has this weight here, with the measure BdB for each of these circles. Okay, so this is a formula for JT gravity. We know the Z trumpets, we don't know the V's. But fortunately, Mirzakhani has a wonderful recursion relation for these volumes. And this recursion relation is going to be basically equivalent to this topological recursion. So it turns out, so these, just the side comment, these volumes, they're polynomials in the lengths of the boundaries. So it's not important, I shouldn't mention that. The rough idea is that if you think about the surfaces with, say, one boundary and two handles, our goal is to understand what's the volume of the moduli space of this surface. And we can think about it as related to the volumes of the moduli space of simpler surfaces glued together in all the different possible ways. So for example, we can think of this surface as formed by gluing together these two simpler surfaces, or by cutting a handle and then gluing these two things together. Now, again, when we do this gluing, we try to create a surface like this by gluing together simpler pieces. It's very, very difficult to deal with this overcounting problem. But Mirzakhani came up with a really very clever way to deal with it and gave some recursion relations, which I'm not going to write down explicitly. I'm just going to say that this is sort of the rough idea, and there's some here's some references if you're interested in learning more. And so this idea of splitting up the surface into simpler pieces, reminiscent of this topological recursion formula, where the resolvent of genus G came from resolvents that were somewhat simpler, but like glued together in some way. And in fact, these recursions are equivalent. And this was proven by Einard and Aranton so the idea is you take the double scaled matrix integral with this spectral curve. Notice this is the spectral curve for the JT gravity density of states. So if you take this spectral curve and you write down the topological recursion formulas, those output these W, these are the resolvents. So there is a recursion relation for the resolvents. If you identify these resolvents as this integral over the B's of these volumes, the recursion relation for these resolvents are equivalent to Mirzakhani's recursion relations for these volumes. Okay, so these unknown things in our formula for JT gravity, there's a way to compute them by using recursion relations given by Mirzakhani, or by using recursion relations from this topological recursion. So let's take our formula for the partition functions, and in JT gravity and in a matrix integral, and we're going to compare them using this formula. So we're going to start with the matrix integral formula for the genus G contribution to the partition function and boundaries. So the partition function we can write in terms of a resolvent like this. We have integrals over the energy with these Boltzmann weights. And let's change variables to this Z from E, so we can make contact with this topological recursion. So we change E to minus Z squared, and we replace this resolvent with these W's. So the partition function is this integral over the Z's of the W's. So W is the thing which in Inard and Orontin related to the volumes. So let's plug in their relation. So this is a partition function of the matrix integral dz's, and now we've plugged in integral db's of these volumes. So let's do the integral over the z's. So the z's appear here. These are the Boltzmann weights. And here in this Laplace transform that related to the volumes of the resolvents. So the integral over z is just a Gaussian integral. The result is e to the minus b squared over beta divided by square root of 2 pi beta. That's just the trumpet partition function. So when we do this, these z integrals, we get trumpet partition functions multiplying these volumes, integrate over b with the weight b db. That is precisely our formula for the genus G partition function in JT gravity. Okay, so then let's take, this is a genus by genus statement. Let's take that statement and sum over genus. And what this is going to tell us is that the partition function in JT gravity, so this is expressed as a sum over topologies, it's an asymptotic series, is equal to this partition function in this JT gravity ensemble, or the partition function in this ensemble where this is the spectral curve. So this thing is non-perturbatively well defined. It's a matrix integral. We can compute all these things, and what we're saying is that this is equal to the output of the JT gravity path integral. So this is the sense in which partition functions in JT gravity are random matrix averages of ordinary partition functions. So each element of this ensemble of random matrices is a double-scaled matrix H, so it has an infinite number of eigenvalues, but each matrix has a discrete spectrum. And so the discrete spectrum approximates, for a typical matrix H in this ensemble, the density of states looks like a discrete approximation to this cinch of root E formula for JT gravity. And then on average, the average density of states averaged over these discrete approximations gives you this continuous function. So this also means that in JT gravity, we should expect the eigenvalue statistics to be exactly given by this random matrix behavior. We've already seen how this cylinder in JT gravity gives the ramp in the spectral form factor. The exact equivalence between JT gravity and this matrix integral means that we expect the sine kernel formula to hold. We expect any sort of random matrix level statistics to hold in JT gravity. So there must be some gravity description of the sine kernel and other things like that. So finally, this also explains some of these mysterious things of why we didn't see any of this noise in the spectral form factor, or why the spectral form factor doesn't factorize. It's because the things that we're computing that we thought were just products of partition functions are actually ensemble averages of products of partition functions. So the spectral form factor computed with the path integral 2 boundaries. This is the thing where we found the ramp yesterday. This thing is in JT gravity is actually computing an ensemble average of ordinary partition function spectral form factors. So the answer for this should be this ramp and plateau without any noise. And notice that this is not equal to the square of the individual partition functions, this one would be computed by a path integral with 1 boundary. This would be computed by a path integral with another boundary. Okay, so maybe actually I have to stop here and say, so this fact that JT gravity, the path integral for JT gravity gives answers for partition functions which look like ensemble averages. This is surprising from the point of view of ordinary ADS-CFT. So usually in ADS-CFT, We know that the CFT is a genuine fixed system. It's got some Hamiltonians. For example, you can take n equals 4 super Yang mills. That's got a Hamiltonian single one. And when you compute partition functions, you just compute trace e to the minus beta h times trace e to the minus beta h, just take a product of those. You don't average over anything. So that's the ordinary examples of ADS-CFT that we're used to, are not these ensemble averages. So JT gravity is different in this way from ordinary examples of ADS-CFT. On the other hand, these things that I mentioned earlier in this lecture, due to Coleman's and Giddings and Strominger, and also more often Maxfield, are suggesting that from the path integral point of view in the bulk, this ensemble averaging is sort of natural. So there's a bit of a tension here between the gravity path integral liking to give ensemble averaging and ordinary ADS-CFT not having averaging. So this is going to be the subject of what Steve Schenker is going to talk about tomorrow. But for now, we're just focusing our attention on JT gravity and seeing what it gets us. And we'll hopefully learn some lessons that will apply to more ordinary examples of ADS-CFT. So finally, so I guess I have 15 minutes left, right? This part I was possibly going to skip, but let's talk a little bit about the some non-perturbative effects. So I'll go back a couple of slides. So we found that this this formula for the partition function in JT gravity, we looked at it genus by genus in this genus expansion. So the genus expansion turns out to be asymptotic. I'll explain a little bit more in a moment. But the matrix integral itself, it's not necessarily defined by its genus expansion. We can take the matrix integral and we can just say for finite L, we can write a convergent integral and it gives an answer. And we can take the L goes to infinity limit of quantities that have well-defined limits, and they should be just non-perturbatively well-defined. So what we're going to do is we're going to take this matrix integral as the non-perturbative definition of JT gravity beyond the genus expansion. And we're going to see what it gives. So the genus expansion in JT gravity, this expansion to e to the minus s naught, is asymptotic. So the coefficients of the genus expansion are related to these volumes, VGN, and they go as 2g factorial. So it's this very rapid growth so that the genus expansion doesn't converge. So typically, if you have an asymptotic series, if an integral has an asymptotic expansion where the terms grow like this, that means you expect non-perturbative effects that go as e to the minus some number times e to the s naught. So this is contrasting with the, like, say we take an ordinary path integral in quantum field theory, and we have a coupling constant g sub c. Ordinary Feynman diagrams give terms that grow like k factorial times g to the k for large k. And through some general facts about how asymptotic series are related to non-perturbative effects, this fact that you have 1k factorial means that you expect non-perturbative effects that go as e to the minus 1 over the coupling constant squared. So this is the typical weight of like an instanton in quantum field theory. So the fact that we're seeing this 2g factorial, and we get an answer that's like e to the minus 1 over a single power of the genus expansion, this is more like what we see in string theory. And that's not surprising because we're summing over these space-times, they look like string world sheets. So if we think about e to the minus s naught as a string coupling, the non-perturbative effects we expect are like e to the minus 1 over g string. Those are the typical weights of D-brane effects in string theory. So in fact, the sign kernel formula that we expect to find based off of random matrix universality precisely has that character. So the sign kernel here has this term which is sine squared of rho times delta E. this is the formula that applies in sort of more general case for a double scale matrix integral. The formula that I wrote a couple of days ago, it was sine squared of L times the energy spacing. But in the GUE, for example, rho total, the total number of eigenvalues, the density at E, is just proportional to L. So we can see they match up in this finite L limit, but this is the generalized case. So rho total in JT gravity is proportional to E to the S naught, this genus counting parameter. So we think about sine as this oscillating thing, it's E to the number times I times E to the S naught. So this is in line with our expectations for the non-perturbative effects, except we have this funny imaginary action for the non-perturbative effects. That means these effects oscillate rapidly instead of being doubly exponentially small in the entropy. So the sine kernel is due to these non-perturbative effects in the matrix integral. This is non-perturbative in the genus expansion of JT gravity. And so the sine kernel it's difficult to see from the genus expansion. There's a possible way to get around it that due to some work by Okiyama and Sakai, where in some limit you may be able to resum an infinite number of terms in the genus expansion to see the plateau. But if we want to study the sine kernel directly, we have to go beyond the genus expansion. And there's a trick which I'll just briefly mention, which is we can think about calculating the resolvent, and we'll do this for two resolvents to get the sine kernel in a moment. We can think about the resolvent in this stupid way. Take the resolvent, multiply it by the determinant of E minus H, divided by the determinant of E prime minus H, take the limit E prime goes to E. Okay, so you might think, how is saying this going to help at all? Well, let's write out the determinant as E to the trace of the log of E minus H. You can write that as E to the something which is like an integral over the resolvent. So then let's expand this thing out, this exponential, and get 1 plus 1 resolvent plus 2 resolvents, so on and so forth. But let's call this integral sometimes T of E. So when we calculate the resolvent this way, and we write the determinants like this, we have a sum over an infinite number of resolvents. So we have R of E times this series in resolvents. So instead of calculating what we thought was a single resolvent quantity, which is described by one boundary in the path integral, we're calculating a quantity that has any number of boundaries. And in the end, when we take E prime goes to E, all the extra boundaries should probably cancel out. So it turns out if you do the calculation a bit of a tricky way, and you calculate with E prime not equals to E, you include all these extra boundaries from the determinants, you sum over all the space-times connecting things, and you try to take the limit E prime goes to E, all these extra boundaries introduced by the determinant don't quite cancel. And they give you they give you a new piece. It gives you a piece which is non-perturbative. In this single resolvent, maybe I should have drawn this. Single resolvent leads to the density of states. So we draw the density of states as a function of energy. The leading order density of states looks like this thing. What we're going to find is non-perturbatively rapidly oscillating pieces in the density of states. So small, rapidly oscillating pieces of the density. This sort of reflects the discreteness of the spectrum. That you have little bumps that are spaced by the average level spacing of eigenvalues. The way in which you get this rapid oscillations is that these extra spacetimes basically exponentiate. So you get an answer which has a term which is like E to the disk contribution of the spacetime. The disk goes like the density. So this is something that's like E to the density of states. So those are the non-perturbative effects that I was just mentioning. So there's an analogous computation for two resolvents where you introduce more determinants. That gives the sine kernel. So this is a bit of a strange way of getting these non-perturbative effects. At least gives some picture, which hopefully there's there's a bit of a unfortunately I don't have much time to go into it, but yeah, so this is an odd picture involving these infinite number of disconnected spacetimes, giving these plateau effects. And because I have maybe
That's about 7 minutes.
7 minutes, okay.
No,
So
10,
I
10
have like
10 minutes.
okay, cool. Yeah, so I'll just briefly say then, add another slide. Along the lines of what we were talking about yesterday, what do these de Bruijn effects mean? Well, so say we are calculating the spectral form factor. And we looked at this contribution where we have one copy of the spacetime and another copy of the spacetime, and they trade a closed universe, trade a little baby universe through this cylinder. What I said yesterday is that the rules for JT gravity are that we don't allow any external baby universe states. So we didn't have something like this. So this is just a rule that we decided on to define JT gravity. We don't have spacetimes like this. Well, so when we tried to equate JT gravity to this matrix integral, perturbatively we summed over spacetimes like this top thing here with no external baby universe states. But then we found this matrix integral definition of JT gravity, and they have these non-perturbative effects where there's a bunch of other boundaries out there introduced by these determinants. So the gravity interpretation of them looks actually more like this thing here, where what we have is, say, our two resolvents, resolvent 1, resolvent 2, and they're allowed to connect to extra space-times that were created by the determinants. They're allowed to connect to them, and these can connect to each other. And we can think about the disconnected pieces here as giving some sort of normalization back. And so there's a way in which you can think about these extra non-perturbative effects saying, well, non-perturbatively, you're allowed to let the baby universes, you're allowed to emit a baby universe in some external state. And the external state is described by the path integral over these boundaries here. So it's not just, you're not picking any random baby universe state by hand. It's somehow coming out of the path integral when you consider these non-perturbative effects. So to go back to our picture of the ramp, we saw that the ramp came from allowing this large baby universe to be emitted that shortens the space-time. So the plateau means that at some very long time, your black hole has grown to a exponentially long length. You can emit a closed universe, a little baby universe, in some state. So instead of trading it to this thing, you can trade it to this guy, or you can emit it in some state. And the state here is correlated with the state here because these geometries are allowed to connect together. And that state affects so it's an additional contribution to the path integral that also is allowed to shorten the space-time. But it comes with a sort of a minus sign, which cancels some of the ramp contribution. So at these plateau times, there's sort of two competing effects. One is this cylinder where you trade a baby universe. Two is these external baby universe states. They both allow you to shorten the Einstein-Rosen bridge and get a non-decaying answer. So that's sort of the most I can give of a picture of this plateau in terms of JT gravity. So now I'll just finish with some ending points. So JT gravity is an example of this general thing talked about by Coleman, Giddens, and Strominger, where space-time wormholes lead to having an ensemble average of theories. And it's very different than ordinary ADS-CFT. So another point is that this plateau was very weird. So it's not simply related to the genus expansion. It has this many extra boundary description. And so we can ask, does that generalize to higher dimensions? I told you yesterday how there's this more general double cone version of the cylinder, which gives the ramp. An open question is whether or not you can generalize this plateau thing to higher dimensions. It may even be that this description I was telling you about in terms of these determinant tricks, maybe not the best way in general to think about that plateau. So there's a lot of questions remaining about the plateau in gravity. JT gravity has allowed us to get some handle on it by this non-perturbative definition of JT gravity via the matrix integral. But in more general theories of gravity, we don't have that crutch of the matrix integral definition. So it's difficult to justify this determinant trick of giving that plateau. Another point is that there's generalizations of this JT gravity dual to a matrix integral phenomenon. For example, if you consider JT gravity with non-orientable surfaces, we only talked about orientable surfaces. I should have been more clear about that. If you talk about non-orientable surfaces, you can find a matrix integral dual which is in the GOE or GSE symmetry class. So those are the other symmetry classes I talked about a couple days ago. You can also look at versions of JT supergravity that have additional kinds of matrix integral duals. So this is from work by Stanford and Witten. Now there's other generalizations of JT gravity where there's you add defects in the bulk, or you can think of those as modifying the dilaton potential. So we gave in JT gravity we had a very specific, finely tuned dilaton potential. There's versions of JT gravity with different dilaton potentials that are also related to matrix integrals, and this is by Maxfield, Tirachi, and Witten. And so there's one big open question, vague open question we're left with, which is, what does any of this JT gravity matrix integral duality tell us about ordinary ADS-CFT? So as I've emphasized, this ensemble average property of JT gravity, we don't think that applies to ordinary ADS-CFT. Well, don't think at least. So for example, a fixed Hamiltonian must have noise in the spectral form factor, or Z beta plus IT. Partition functions must factorize. So this is in tension with these wormhole effects that we found. So just to sort of make some progress towards understanding this, a way to model a fixed Hamiltonian from ADS-CFT might be to draw a typical H from the JT gravity ensemble. So in JT, we can take the JT gravity matrix integral, and instead of averaging over the matrices, we can say, let's pick a typical H in the ensemble and calculate the spectral form factor. That should give a noisy function with an average ramp and plateau when you time average. So maybe the behavior of that is related, would be able to teach us something about how the spectral form factor behaves for a fixed H in ADS-CFT. So there's some ways of representing these fixed H versions of JT gravity in the bulk by eigenbranes. And there's a way of thinking about that as allowing us a more complicated background state of the baby universes. So if you have a specific H, you calculate in JT gravity where you do the ordinary path integral, but you allow baby universes to be emitted and absorbed in sort of random looking states. And those random states give the noise in the spectral form factor. And so there's a lot of recent work about this. And this is basically going to be related to what Steve Schenker is going to be talking about tomorrow. Okay, so that's it for what I have to say. But so finally, I'd like to thank the organizers of TASI for bringing this all together and making this great. So yeah, thank you, and thanks for listening to my lectures. Hope you enjoyed them.
Thank you very much, Phil. Wonderful. So questions for Phil. This is your last chance.
Ask something. Is there a Hamiltonian quantization of JT gravity that's equivalent to this double-scaled matrix integral thing, like what Harlow and Jafferis did for the two-boundary case?
I don't think so. Yeah, and I think it's because in the Hamiltonian quantization, it's hard to incorporate these closed universe effects. I'm not sure. I don't understand it well enough to know whether it could be done, but yeah, the short answer is no, because of the absorbing and emitting closed universes.
So is there a sense of asking about, let's say, the alpha states and their analogs for JT gravity, the kind that Coleman, Giddings, and Strominger got?
Oh yes, there is. Those are related to these eigenbrains, and the way you can think about that is sort of in the path integral perspective. It's sort of straightforward to allow closed universes to be in some specified state, in the alpha state, because you can represent that the alpha state of the closed universes in a basis of like you can create that state in the path integral by boundary conditions in the path integral. So you can include this alpha state without needing a conventional Hilbert space quantization of the JT gravity.
Yep, thank you.
Other questions?
I have a question.
Go ahead.
So I'm a bit confused about these D-brain effects. So I'm not sure exactly how to think about them, like in terms of the actual geometry. Is it somehow what you're doing is, like, for example, for just a disk, you have this this boundary curve which has a Shortsian, which is governed by these Shortsian dynamics, and then you sort of go deep inside the disk, and then you put a brain in there, and that's what these D-brain effects are.
So maybe here's a where. So let's make the analogy where if you're calculating the resolvent or partition function in JT gravity, it's similar to calculating an amplitude with like an external string in string theory. So we have a boundary that's the final state of the string, and we sum over the things where maybe a string can nucleate and end on there. That's the disk. If we have a D-brain, then there's strings can end on this brain. So we can have a thing where the string comes from the brain and ends in this final state. We can also have strings which live on the brain, or something like just a disk. So the picture in string theory is that there's these disconnected world sheets that live on the D-brain, and there's the world sheet with your like external state can connect to the D-brain like a cylinder. So in JT gravity, we're thinking about it in a slightly different way, where we're now, instead of thinking about this as an external string state, we're thinking about it as like a partition function, or if we calculate the spectral form factor, we can think about it as one of these amplitudes where we evolve the thermal field double state. In that case, this cylinder connecting to the D-brain, we can think about it as, well, this is one way to think about it, is as there's some space-time D-brain out there, and it's allowed to create closed universes. So instead of creating strings, it creates closed universes, and the closed universe is absorbed by the space-time. It can create them, or it can absorb closed universes, which are emitted by this. So that's the way I like to think about it, is that these D-brain effects, they create or absorb closed universes, and those can interact with our black hole.
Okay, so if I were to throw a particle into a black hole, it would disappear behind the horizon and end up in one of these baby universes.
So it could be, so this, if you throw in a particle, it can be taken away by a closed universe, and then the closed universe can end on a D-brain. So it's like a D, it's like a, the D, there's no sort of ambient space-time here. These strings live in a target space. Here we're not really thinking about a target space. So this D-brain doesn't live, so it's not an object that exists in time or whatever. So you can think about this as just a final state for the space-time instead of ending on an object or whatever. So if you throw a particle into the black hole, it can be absorbed into a closed universe, which pinches off and ends in some state described by the D-brain.
Okay. And can I just follow up with one more question? So all these wormholes, you've described them in a Euclidean signature.
Yeah. Mhm.
So is there any like sensible way of thinking about these geometries in a Lorentzian signature?
Yeah, so this is tricky because so there are ways, and sort of like what we were seeing yesterday, it's not quite unique. There's different ways of, if you take, say, the calculation of z of beta, which is a Euclidean space-time calculation, and you continue beta to beta plus it. One way to think about it is the way I described yesterday, where z of beta plus it is like one of these amplitudes evolving the thermofield double. And then there, the geometry has pieces of Euclidean and Lorentzian space-time, or in general, you'll have pieces that are complexified. And there's a lot of freedom, basically like a gauge invariance, choosing how to describe these spacetimes. It's different. There's different complexified spacetimes that give the same answer, basically related by gauge choice. The way I like to think about it in general is, if I'm calculating something like z of beta plus it, I have the Lorentzian stuff going out near the boundary here. So I like to think about these amplitudes, and then all the higher genus stuff I like to think about as I've emitted a closed universe, and somewhat like how in quantum mechanics an instanton process is described by Euclidean path integral. This baby universe emitting is sort of like a tunneling process, and you can think about it as described by this smooth Euclidean geometry, but in Lorentzian signature, it's like a instanton pinching off effect. So maybe that's how I sort of like to think about it, but there's a lot of freedom, so it's really unclear what the sort of right way to is.
Okay.
Just one side comment, actually, briefly, is that these closed universes, they have constant negative curvature, so they have big crunches and big bangs if you continue them in time. So we've drawn them on these Euclidean slices, but if you evolve them forward in time, they have big bangs and big crunches. Yeah.
Thank you.
Can I ask a follow-up question about this?
Mhm.
So this could be totally out there and just the wrong way to think about this, but the discussion you were just having made me think of this. So is there any way I could think of these D brains that you were just talking about as being like a reservoir or a bath for these baby universes? And if that's the case, is there in some sense a way that the system, say, comes into equilibrium with the bath, that the rate of absorption and emission kind of equalize?
I'm not sure if there's really a way to think about it like that. It's maybe more accurate to think about them as some. I think maybe it's more accurate to think about it as a external state of many closed universes, and it's like the number of closed universes is any number of closed universes, because the D-brane can create or absorb any number. And so when you absorb a closed universe created by this D-brane, the D-brane still has an infinite number of closed universes that it's created. So there's maybe that's closer to the picture that you have in mind, but yeah.
Yeah, it was a little off topic, but thank you.
Yeah, I'll say one thing is that I suspect, and this is we don't totally understand this yet. I suspect personally that the right way to think about these D-brane effects would take advantage of this notion of an alpha state that someone earlier had mentioned. the alpha state, I haven't explained it, but it's related to what happens if you don't average over the Hamiltonians. That involves having some background state of closed universes. The proper description of the D-brane effect, I suspect, is more natural when you take those sort of ideas into account. But yeah.
Okay. Thank you.
Any other questions?
Yeah, I had a question about something that you talked about long ago in your lectures. So when you wrote down the JT gravity action, you chose the term with the scalar as r plus 2.
Yeah.
So I guess that was because you wanted to have a constant negative curvature bulk spacetime.
Yeah.
But is it possible to write down an action with a positive curvature?
Oh, yeah. To like the de Sitter JT gravity.
Yeah.
People have studied this, and actually, there's some way that you can think of. There's a matrix integral description of amplitudes in JT gravity and de Sitter. So you have an initial state and a final state of de Sitter universes. And the de Sitter universes can join and split. And those amplitudes are really just like an analytic continuation of this matrix integral. And this is work due to, I think there were a couple of papers, one by Kotler and Jensen, another by Maldacena and Yang, and I think Turiachi. Yeah, so there, I don't really understand that too much, but short answer is I think yes, you can study JT gravity with positive cosmological constant, and you can use this matrix integral relation to study it.
And is that, I mean, people have done that only in 2D or in higher?
Oh yeah, sorry, just in 2 dimensions. So all this JT gravity matrix integral stuff, in this precise relation between a path integral for gravity and a matrix integral, this is all special to JT gravity and generalizations of it. We don't have there's no other examples that we know of. There's some progress on trying to understand versions of 3D gravity as other ensemble averages, but the thing we saw today is somewhat special.
Okay, thank you.
Anything else?
Ask one more.
Go ahead.
So in this Maroff and Maxfield paper that you mentioned, they, in the Hilbert space that they obtained with the alpha states, their Newton's constant was no longer a free parameter in that Hilbert space. But this is kind of a qualitative difference from JT gravity. So would you expect that JT gravity can be completed into some structure which no longer has this qualitative difference, or can Maroff and Maxfield never bridge this gap with JT gravity?
Yeah, so that's so yeah, in that sense, Maroff and Maxfield's model is qualitatively different than JT gravity. So it's not like you can't think of it as like a continuously related to JT gravity, for example. But besides that fact, a lot of the so their formalism that they describe with the alpha states is general, and it doesn't require that phenomenon that they found in their toy model. So they'll basically, the language of alpha states and everything like that, some of the results still apply to JT gravity, even though their toy model and JT gravity do have this very interesting qualitative difference. I'm not sure if that answers your question, though.
Yeah, it does.
Okay.
No, thank you.
Any final question? Okay, so if not, then we can stop the recording and thank Phil